Our first speaker is Gerard Misiolek from Notre Dame, speaking about geometry of diffeomorphism groups and H1 optimal transport.
It's a great pleasure to be here, participating in the conference, honoring Dennis Sullivan. And it's also great to be back in Stony Brook and see how it has changed, especially in recent years. The title and abstract of my talk include words like diffeomorphism groups, optimal transport, and statistics. But the main object, the main character will be a certain nonlinear partial differential equation, which arises in a similar way to the Euler equations of ideal fluids that we heard about in the previous two talks. So it's the same Arnold formulation, Arnold framework. Since Arnold's paper, which appeared in the Annals of the Institute of Fourier, Grenoble, in 1966, a number of nonlinear PDEs broadly speaking, of interest in hydrodynamics have been recognized as geodesic equations with respect to various various metrics on different diffeomorphism groups. And the metrics that I will be interested in this talk are of Sobolev H1 class. And these metrics include, they will be right invariant metrics, and they include, I will explain, of course, what I mean by, I'll write down the metrics later on during the talk. But such metrics, they yield as geodesic equations, or the Eulerian Arnold formulation, corresponding nonlinear PDEs. For example, the one-dimensional, completely integrable systems of shallow water theory. So examples here are the so-called Kamasa-Holm equation, or the Hunter-Saxton equations. So these are equations in one space dimension that are very similar to the so-called, much better known, Korteweg-de Vries equation. So this is like the most important, I think, of the one-dimensional integrable equations. It has very nice bi-Hamiltonian structures and infinitely many conserved integrals. And these other equations that I mentioned also have these features. But in higher dimensions, the H1 metrics also produce equations that are of some interest in fluids. For example, the so-called Euler alpha or EP-diff equations, which are thought to describe motions of so-called second-grade fluids. So there is some interest here. Okay. On the other hand, that's a kind of slightly different story. H1 metrics can also be seen as arising in a natural way on diffeomorphism groups, as arising in a natural way as induced metrics on the orbits of the diffeomorphism group, which acts by pullback on the space of all Riemannian metrics. And when the space of all Riemannian metrics, at least on generic orbits, when the space of all Riemannian metrics is equipped with the L2 or trace metric that, for example, David Eden studied in connection with the slice error. So, but as I said, this is a different story. Now, in my talk, I will be interested in one such H1 type metric, and in order to explain, to make the connections with these various fields that I mentioned earlier, I will start with the kind of bigger picture in the L2 case. So let's imagine that this represents the group of diffeomorphisms, diff of M, where M is Mn is a compact a Riemannian manifold. And I assume that it has some Riemannian volume form which will be fixed. So this is volume for mu. Now, we'll also be interested in the subgroup of diffeomorphisms preserving volume mu of M, that's diff mu, which already appeared in the previous talks. So, okay, so these are all diffeoms. These are volume preserving diffeoms. And I want to consider this as a principal bundle, this being the structure group. So there is a base here, which is a quotient of diff by diff mu, and we have a projection. So this is eta here, a diffeomorphism. It's projected. Let me call the projection pi to say pi of eta, which I will write as rho. This projects, say, to 1. Okay, and I will put different metrics here. So let me write the metrics that I'm interested in. And as I said, I'll start with the L2 case. So on the total space, on the diffeomorphism group, on diff of M, I will consider the L2 non-invariant L2 metric. And let me write this down. So say if eta is a diffeomorphism of M, and say capital V and W are two vectors tangent to diff M of eta. So this I understand this as sections of the pullback bundle. The pullback is by eta of the tangent bundle to M. So these are vector fields along eta. So I take two such elements here and define the product, the L2 product at eta to be the integral over M of V. So this here I'm using this pointed bracket means the Riemannian metric on M. And this is evaluated in the tangent space at eta of x. And then I integrate this with respect to the fixed mu form, volume form. Okay, so this is the metric on L2. Sorry, on the L2 metric on diff. Now on the subgroup, it restricts to, so on the subgroup of volume preserving diffeomorphisms, this metric restricts.
You integrate with respect to mu or with respect to its eta image?
No, mu. So it restricts to, let's see, on diff mu, it restricts to the right invariant metric, L2 metric of the ideal fluids that we had about. Okay. So this is, of course, the situation that what was described by Arnold. That's the 1966 paper. And let me actually immediately here point out that in order to make good sense of these objects as manifolds, smooth manifolds, one needs to topologize them somehow. So one possibility is, of course, using the HS Sobolev topologies, and I will not discuss that. I'll leave this aside. I'll concentrate on the geometric part. But let me just point out that the analysis, for analysis, I referred to the paper of Eben and Marsden, and the analysis can be done in very much the same way. So this is a 1970s paper. One can also use the framework of Omori, of the so-called inverse limit Hilbert spaces, but it won't really matter for us. So these are the metrics. Now on the base, there is also a metric on the base, on the quotient, diff m by diff mu, Now, here the story goes like this. About 10 years ago, Felix Otto, while studying certain nonlinear heat equations on the space of probability distributions, heat equations and for example, the porous media equation, he wanted to study them as gradient flows. He needed a metric on those spaces of densities, and what he did was introduce the following metric. So let me begin. Okay, I can do it like this. So this is Otto, paper in Communications of PDEs from, I think, 2001. So let's first take a row, that's a point in the base, which we will think of as densities. So these will be, say, smooth densities, positive row functions on M, such that they integrate with respect to the fixed mu to mu of M. So for probability, in the case of probability densities, one would, of course, take the 1, but for us it can be just mu of M. And then if we linearize this, then we see that the elements of the tangent space at rho will be functions on M, mean zero functions, right? Whose integrals with respect to mu would be 0. So if I take two such, say alpha and beta, so these are two vectors tangent at rho, then he defined the metric as follows. So I take alpha product with beta, this is at rho, and the definition is that this is given as the integral over M of, now here I take the product of the gradient of function f with the gradient of g times rho and integrate it against d mu, where I need to explain what f and g are. So these are functions where f and g are functions on M, such that let's see, the divergence of rho times the gradient of f is alpha. This is how alpha is defined. And similarly, the divergence of rho times gradient of g is beta. Okay, so Otto introduced this in 2001. So this metric on the base is compatible with the L2 metric, this non-invariant L2 metric on the total space, in the sense that the projection here, which by the way he considered the projection to be Jacobian with respect to the fixed mu form, volume form, so the projection rho is given as Jacobian with respect to the mu of eta inverse, that this projection becomes an infinite dimensional Riemannian submersion. So in particular, pi star at eta is a surjective map, and when restricted to the horizontal space, at eta is an isometry with respect to the metric. So here is Otto's metric on the base and the L2 non-invariant on the total space. So this is an isometry. It's like an infinite dimensional submersion. So let me just also add here that the horizontal space here at eta can be thought of as essentially as gradients of f of functions on M composed with, or right translated to that point, and the vertical then, so this is Hodge decomposition in the background. So vertical at eta will consist of all those compositions B, right translated to eta, to the point eta, B composed with eta, such that the divergence of rho times B is 0. Okay,
so does it follow from sort of a priori from the fact that the metric is right, the big metric on the big space is right invariant, but there will be some metric downstairs with respect to which this is a Riemann submersion?
For L2.
And then this results in a computation.
For L, yeah, if we take L2 metric on the total space and it's right invariant, it will not drop down. I don't know how to see it.
Riemannian
No,
conversion.
no. But the one that I will describe, which will be H1, will be.
Oh, okay.
Yes, so
Well, the first building is there, and then you have a...
yeah.
What do you...
Well,
you said it's a Riemannian subversion, so that suggests there was a metric upstairs.
yeah, there is. The metric upstairs that I'm using here, that Otto used in establishing the submersion, is precisely this one. It's not invariant. It's not right invariant. Okay, so it's defined in this way. It's not a metric which is defined, say, the tangent space of the identity, and then right translated to the whole space using the group strategy.
There's an eta there. I didn't see that eta.
Yeah, there is an eta. Yes. So, okay, so let's see, what I wanted to say here is that, first of all, this is a picture that Otto developed because he was interested in studying certain PDEs on the space of densities, but he noticed that there is this Riemannian submersion property, and there is, however, more to it. Namely, there is a connection, there is a certain link to optimal transport. So let me explain this. Well, it turns out that, which was actually a result that was perhaps first suggested by Benamou and Grenier, even before this paper of Otto's appeared. So, sure.
So many formulas I can't remember. So I didn't say the right thing. So this metric is invariant under the fiber structure.
Yes, it's invariant on the fiber. It's only right invariant on the group of volume preserving diffeomorphisms.
So therefore it is a Riemannian subversion because of that.
Right.
And then there is
Yes.
some metric on the base for which it's curvature, and then you're computing what it is.
That's
metric is computing
right.
what this induced metric is.
That's not my understanding. It's not how Otto worked with this, but that's that's how it.
Know why he did it. I mean, I'm just saying that a priori there is a metric because it's right invariant to the fiber group. There is a Riemannian subversion. So
Right.
there is some metric.
Right.
I mean, you want to describe it.
Yeah.
But then you said the H1 metric.
H1 metric, the one that I will introduce, will also descend to the yes, to the quotient. So this is a kind of H1 analog of this picture, which is what I'll try to develop. So okay, so we have the metrics here, and there is the link to optimal transport, which goes like this. So it turns out that the Riemannian distance of Otto's metric on Diff mu coincides with something which is known in optimal transport in general in probability theory, known as the Wasserstein distance. So of optimal transport. So let me write this here. So it's the distance here W between two, say, densities, rho and lambda, is obtained by taking the infimum over all etas, so these are all diffeomorphisms of M, which take, say, lambda to rho, this, they pull back one density to the other, of the integrals over M, of the distance, now this is the square of the distance, Riemannian distance on M, between x, the point x and eta of x, and this is integrated with respect to mu. Now, as I said, optimal transport here, the connection really goes way back. So the names that are associated here are those of Monge and Kantorovich. And in the classical formulation of Monge, the way one interprets here this object is as follows. So eta here is thought of as the so-called transport map, which, well, we can imagine that we have a manifold M here, and we have, for example, Earth, and we have two piles of sand. So there is a one pile, rho, and there is another one, lambda. So these are piles of sand. And this Monge problem, one looks for a map, a transport map that minimizes the cost function, so a quadratic cost, which is described by, this is how one interprets this integral. Actually, wait a minute, this is, so here I'm kind of pulling back eta to rho. I think in optimal transport theory, they usually work with the push forward, I think, from rho to lambda. So this is a pullback by eta inverse. So I think this is usually in terms of push forward how this is described. Okay, so this is the link to optimal transport, and therefore one can kind of think of in this setup, M2 setup, the fiber, the geometry on the fiber is really the ideal fluid geometry. And here one has this optimal transport. Okay, now my goal here is to try to develop similar picture for replacing this metric with another one, and that other metric will be of H1 class. So let me now try to describe it. So first, let's consider, so this will be a right invariant metric. So I will consider just the H1, the Sobolev H1 inner product on vector fields on M. So suppose that V and W are two elements of the tangent space here at the identity to the whole diffeomorphism group, and the product here, the H1 product, will be defined as follows. So I will introduce some parameters A. So I'll start with the L2 part, and then there is the H1 part, which I will now also break up into two parts. So probably I'll switch here to differential form notation. So I'll take delta and the musical isomorphisms here. So it's a V flat and delta W flat, these are the one forms. D mu plus C, this is the third part. So here I take D, the exterior differential of V flat and dW flat d mu. So this is the L2 part. Here is the H1 part, homogeneous H1. H1 dot usually is of the H1 metric. Now then what one does is one obtains a right invariant metric by right translate to get a right invariant metric on whole group diff of M. Going back to what I was saying earlier, as special cases, one here obtains, for example, starting with this metric, one obtains one can obtain different nonlinear equations of hydrodynamic of relevance in hydrodynamics. So, for example, if just to mention, if B and C are 0, and we're on the subgroup, we restrict to the subgroup, then of course we get the Euler equations of fluid dynamics, of hydrodynamics. Now, there was a mention earlier of the Berger's equation. So if B equals C equals 0, and we stay on the group, the bigger group of all diffeomorphisms, then we get the right invariant n-dimensional Berger's or pressureless Euler equations. And one gets also Euler alpha or EP diff equations in this way. But the ones that I'm more interested in at this point are, again, something that I mentioned earlier. What happens, the equations that we obtain when n is equal to 1, and these completely integrable equations of the shallow water theory. So let me actually specify the one that I'm interested in. So in the one-dimensional case, we will be looking at periodic equations. So the total space here will be the diffeomorphisms of S1. And if I take A to be 0 here, then, well, there is just one homogeneous H1 dot part, namely just the integral of the L2 product on the derivatives. So what the equation that one gets is the so-called integrable periodic Hunter-Saxton equation. Now, this equation has been proposed by derived by Hunter and Saxton in the context of liquid crystals, and this, I think, goes back to 1991. Its integrability, its Hamiltonian structures, bi-Hamiltonian structures, were studied by Hunter and Zhang, I think, in 93 or 94. Now the equation looks like this. It's an evolution equation. I mean, one can view it as an evolution equation, but it's usually written in this form. So u here is a function of two variables, t and x, and the equation looks like this. It's a time derivative followed by two x derivatives plus 2ux uxx plus uxxx, and this is set equal to 0. The Cauchy problem for this equation has been also studied quite extensively. So local compositeness is known in some Sobolev spaces, Sobolev framework. Usually one works here with the spaces, Sobolev spaces with the Sobolev index greater than n over 2 plus 1. So in this case, when n is equal to 1, this is s is greater than 3/2. One can also obtain results on the breakdown of finite time blow-up of solutions here. And the equation that I'll be interested in will be a sort of generalization of this equation. So let me go back here for a second and tell you what is precisely the object that I'll be interested in, and it's this part. So I will call the H1 dot metric the degenerate right invariant metric on the diffeomorphism group, which comes from right translating just this part. So this is the part corresponding to A and C being 0. In fact, I will also pick a very specific B, and well, I'll rewrite it as in terms of vector field. So this will be integral over M of the product of divergences of V and W with respect to mu. Okay, and this will be the main object of interest. So as I said, this leads to a degenerate A equal to C equal to 0, degenerate right invariant metric. Now, the results that I want to describe, I'll state them as a theorem, are, well, this is a part of a larger project in collaboration with Boris Hessing, Jonathan Lennels, so it's myself and Steve Preston. And they, well, they're really quite new. So let me now describe the results. So Mn, as before, is a compact Riemannian with fixed volume form mu. And the statements that I will try to describe are the following. So first of all, and this goes back to what I mentioned earlier, we have that the this object here, which is which we can think of as the degenerate right invariant metric, on when considered upstairs on the total space, it drops down to a non-degenerate right invariant metric on the base. So the degenerate right invariant metric, or let me be more specific, A equal to C equal to 0 metric on diff of M descends to a non-degenerate right invariant metric. I'll call this H1 dot metric on the quotient over diff mu. So this is the first statement. Then second, one can derive the corresponding geodesic equation on the quotient space, now viewed as an infinite dimensional Riemannian manifold with the H1 dot metric, and obtain the corresponding equation explicitly, either as a geodesic equation on the quotient space or as a PDE. So I'll write the PDE version. So the associated Euler, sometimes called Euler-Arnold equation on the quotient reads as follows. So here rho is a function of Tnx.
Wait, is that defined?
Yes. Well, you can, yeah, so you have to just think for the way I want to think about this is think here on this space as an infinite dimensional manifold. So this is all the rows such that these are the densities. And I'm looking at this space as a Riemannian manifold with the metric which comes from the H1 metric upstairs. The geodesic flow of that. But right, so what I write here is dt rho plus the gradient of rho in the direction of u. I'll describe the connection. Plus 1/2 rho squared plus 1 over 2 mu of m times the integral over m of rho squared d mu is equal to 0. Where the connection between rho and u is that rho is a divergence of u. So u is a vector field on the manifold. Now, if we add to this we make this into a Cauchy problem, an initial condition, then what we get is, a problem which can be studied. I can look at well-posedness of this equation, and global and local, and the results are the following. So first of all, star is locally well-posed, which is abbreviated like this. And this means it's locally well-posed in the sense that one can construct local in time solutions given the initial condition here in HS. So it's a Sobolev space. For sufficiently large S's, I can construct a solution which is unique and depends continuously in the Sobolev norms on the initial data. So this is one result. Then it turns out that all smooth solutions, or strong solutions, of this equation, of this problem, blow up in finite time, break down, blow up in finite time in the following sense, namely, there exists a time, some maximal critical time, such that as we approach this time, then the L infinity norm of rho, or C1 norm of u, grows without bound. Now, these two results are very much like what one obtains for the Hunter-Saxon equation, the one dimension. Furthermore, there is also a following statement, namely that this this equation here is also integrable in the same way as the one-dimensional Hunter-Saxton. So star is a completely integrable system. It's a completely integrable system in any dimension n. Now, there are not many completely integrable equations in higher dimensions. So there is Kalonzin-Petiashvili, the variant of Kalonzin-Petiashvili. There is the Ishimori system, Davis-Stewartson, I think Young Mills also. So there's something here special, and of course one way to look at it is somehow by comparing the one-dimensional case, and this is what I'll try to do. Okay, so this is the second statement. There is one more that I would like to include here. Perhaps I'll do it here. And this is a little surprising, at least to us, when we studied this. So that's part 3. Well, it turns out, I'm now looking back at the connection to optimal transport in the L2 case. So what happens here is that one can also compute the Riemannian distance of the H1 dot metric on the quotient. And it turns out to be something that's known in probability and in statistics. So that's the connection to statistics. It turns out that this is the so-called spherical version of the Hellinger distance, which is one of the distance functions that are considered in probability and statistics, are used widely in probability and statistics on the space of probability.
Computing the global metric now.
Right, I'm computing the distance function. Right. So, right. So this is it's spherical. Let me write this in. Hellinger distance, and I'll define it. So this spherical Hellinger distance looks like this. So this is this sub h. Again, I will take two probability densities. Rho and lambda, and this is defined as the square root of, well, they don't have to be probability, they're just densities on m. So this is square root of mu of m times arc cosine of 1 divided by mu of m times the integral over m of the square root. Now rho and lambda are functions, so I take the product and I integrate these. So this is something that's known. Known in statistics and used, just pretty much like the concept. Okay, so what I will now like to do is to give some idea of how these things can be obtained. So let's see, perhaps I can use this. Now I really would like to concentrate on a few interesting aspects. I cannot discuss everything, so let me be perhaps, but I still would like to say something about each case. So, not much time. So, okay, let me just say the following: that when it comes to this statement, this is pretty much like in finite dimensions. When one has a Lie group G and a subgroup H, then one can consider the homogeneous space, and the G invariant metrics on the homogeneous space correspond to add H invariant inner products on the corresponding algebra. So you know, one can, for example, here what one can do is check the little add, the skew symmetry of little add with respect to H1 dot metric, and this calculation is pretty much as in finite dimensions. So this is as in finite dimensional geometry. So I won't go into this. Now, so there will be two things I want to say. So first of all, the derivation of the geodesic equation here of star is can be done, for example, in the Arnold's framework. So derivation of star, just like for fluids or the equations that the Hamiltonian or the symplectic fluids. So this is done using Arnold's framework. Alternatively, one could, so this would amount to computing the co-adjoint representation with respect to the H1 dot inner product. But alternatively, one can look at it. One can derive these equations from first Riemannian principles. So we have a smooth manifold. Imagine this is an infinite dimensional smooth manifold equipped with this H1 dot metric. We can consider the corresponding energy functional, write down calculate the first variation formula, and read off the geodesic equations, and we will obtain this equation. So, so this is all I will say here. Now, regarding these results here, these statements, they all follow. So local multiplicitous, blow up, and integrability. The essential ingredient here is the following result, which is, I think, of interest in its own right. And it says the statement is the following, namely there is a map, we'll call it capital Phi, which goes from Diff, from the diffeomorphisms, to the sphere in L2. So these are all the L2 functions on M, with I'm taking the volume form here, d mu, such that the integral of f squared with respect to mu is equal to mu of that. So that's the square root of that is the radius. So this is a sphere in L2. You know what? I'll put the in fact, so this is what puzzles myself. I'll put the S's. I'll put the Sobolev context here, so the Sobolev spaces. So then one has to take the intersection of this space with h s minus 1 functions. This map given by, so I'll describe it as phi eta, and this is just the square root of the Jacobian with respect to mu of eta. This map induces an isometry from the quotient diff by diff mu to an open subset of the sphere in L2 and intersected with these h minus s minus 1 functions. So of an open subset of the sphere S, so that's really this sphere right here. SL2, 0, the square root of mu of m, that's the radius. So I take this sphere, and then for HS statement I'll intersect it with.
For your one measure.
Yes, yes. So this is isometry. Right. So this here I have the H1 dot metric, while on this side I have the induced metric from L2. So I'm looking at the sphere with the round metric in infinite dimensions, right? Induced as a submanifold. Okay, so let me say a few words about this.
The H1 metric is being induced by the action of diffeomorphism.
Well, okay. So here is So here is what the statements here, well, one, first of all, has to show that this is well defined, that it maps from the correct space. This is really something that follows from the properties of the Jacobians. So, for example, one computes the Jacobian of C composed with eta. Say I multiply this by mu, so this is C composed with eta pullback of mu, so this is eta pullback C pulling back mu. If, say, C is volume preserving, then this is just mu, and we get the Jacobian of just eta. So it's these type of considerations that are showing us, telling us that this map actually drops. So it maps from the correct space. That it maps into the correct space, well, all we need to do is integrate this mu, and we immediately see that this is my definition here. I put the Jacobian, and not just mu of m. So it also maps into the sphere. Now, then one again uses properties of Jacobians to show that this is injected, and the local isometry. So for local isometry, so this is the calculation here. In order to show that, one has to compute phi star eta. And for example, I'll evaluate it at v composed with eta. So this is an element of the tangent space upstairs, which is v is an element of the tangent space of the identity. And eta is a diffeomorphism here. So if I evaluate this, and I'll take another such. So here I take the W, and now I look at the L2 product of these two. So well, I have to compute what these guys are, and for example, if I just look at one of them, then what I see is, well, I have to differentiate that square root. So, for example, in this case, I get 1/2 Jacobian mu of eta to the minus 1/2 times the derivative of the Jacobian in eta. Again, that type of calculation will, if I multiply the Jacobian by mu, and I will recognize this as a pullback by eta of the volume for mu, then its derivative will involve the pullback of the Lie derivative. Now, when I evaluate phi star at vectors of this form, then what I'll obtain is the divergence of v, the whole function here composed with eta, and this will be multiplied by the Jacobian, by the pullback by eta of mu, which gives me the Jacobian of eta. So this is really, this is multiplied by mu, but I'll drop the mu. So this is the derivative here. If I do the same thing in this case, then a little computation and change of variables will give me this result. So this is, if I, well, with or without, before even changing variables, I'll get this product. And this is times Jacobian mu of eta, which I'll now recognize with the correct scaling as the product of v and w with respect to h1 dot metric. So local isometry is obtained in this way. Now, so what the corollary, as a corollary from this result, we get the following statements. So first of all, the space, this quotient space, diff by diff mu, with the right invariant h1 dot metric has positive constant curvature. It's Geodesics. It's Geodesics. Geodesics of this metric of h1 dot metric on the quotient, they correspond to great circles on the sphere SL2, So this immediately tells me that I can get very nice expressions. I can essentially solve the very explicit, obtain very nice explicit expressions of the solutions to the nonlinear PDE, and let me write them. So geometry kind of helps here to really solve this problem almost very explicitly. I have to tell you what eta here is. So solutions of this Cauchy problem with rho 0 as the initial data can be represented as follows. So this is, let me just make sure that I get it correctly. So this is 2c, c is a constant, times tangent of arctan of rho 0 of x, so this is the initial condition, divided by 2c minus c times t, where c is squared as a constant, which is explicit, and it depends only on the initial datum. So this is rho 0 squared of x dx, or d mu of x. And eta, or eta of t, is the flow of the vector field u. From this representation, I immediately obtain the maximal time, existence time. This is where the blow-up statements come in. So I have to look at where this becomes unbounded. So I take, for example, from here, all I need to take t to be is pi over 2c plus 1 over c times the arctan. And here I take the infimum over x is in m, so I'll take the first x, the x where this is achieved of, well, I can switch to using the vector field u0, this divided by 2c. So this will be the time, existence time, the lifespan of these solutions. Now, another statement that comes out very quickly is the one about complete integrability, because what this is telling me is that the integrability.
What was the density function of this point? What is rho?
Oh, rho is the solution here. It's the divergence of u. So, integrability now, my statement here about integrability, let me just say that this integrability of this equation, of this nonlinear PD, now can be thought of as integrability of the geodesic flow on an infinite dimensional sphere. So one can, in fact, write down the infinite sequence, explicitly, infinite sequence of commuting integrals, first integrals, nice Hamiltonian structures, although not so easy to obtain. Okay, now let me move to, in this remaining few minutes, to the part 3, the connection with Hellinger. Okay, so in statistics, one considers the following object. So let's let rho of, so this is rho with parameters t1, tn, rho of x, be a family of smooth, I'm only considering the smooth, I'm working with the smooth category, of smooth probability distributions on the manifold M. So here x is a point on M, and t1 dot tn are statistical parameters. Now, in this case, in the geometric approaches to statistics, people usually view this as an n-dimensional manifold. So it's a finite dimensional manifold, S, called the statistical model, or the statistical manifold. And this point of view can be found it's pretty standard in books. For example, Amari, Nagaoka, or even earlier, book by Chen Tsoff. So these are translations from Japanese and from Russian in 2000 and I think even in the 1990s. So this is viewed as a smooth manifold. It's an infinity manifold. So that's precisely rho, T1, say Tn, where the local coordinates are basically given by the statistical parameters. T1, Tn are, say, real numbers. Now, as an example, one can consider, so let's take M to be R, N to be 2, that's two-dimensional. Let's take T1 to be mu, the mean, and T2 to be sigma, which is, what is it, standard deviation, I think. And then one such family, example of such family would be given by the normal distribution. Family of rho of, say, let's write it as x, mu, and sigma, 1 divided by the square root, I think, of 2 pi times sigma, and then we have e to minus x minus mu. So this is something that's 2 sigma squared, I think. So this is one example. Now, in the 40s already, people understood that one can define, given such a family, one can define a non-degenerate positive definite matrix associated with this family, which is called the Fisher-Rao information of the family of distribution, family rho. So this is usually denoted as I sub ij of rho. I and j span the set from 1 to n. So that's the Fisher-Rao information, which is defined as integral over m. And here we are integrating the derivative in, say, ti of the logarithm of the density times d over dtj log of rho. Rho depends as a function of t 1 to tn, and of course also of x. So this is multiplied then by rho and then integrated around with respect to the fixed volume form. So this is known as the Fisher-Rao information, and I think it goes back to perhaps Rao and also Kolmogorov, who had a very lively interest in geometrization of statistics. And this is 1940s, when they observed that this matrix, n by n matrix, ij from 1 to n, can be viewed as a Riemannian metric on the statistical manifold Sn. That's associated with that family. Okay, so here comes the connection to the geometry that I was describing. Namely, it turns out that if we now view this, if we look at this Sn as, take the inclusion map here, as included in the space of densities, over diff mu, and if we take the H1 dot metric here, let me call this G, that's the H1 dot metric, G sub H1 dot. And on this side, we take the Fisher-Rao, the metric here defined by the Fisher-Rao information. Then, well, one actually gets, this is a restriction of the H1 dot. So, in other words, one can view this H1 dot metric, right invariant metric that we dropped from the big space of all diffeomorphisms to that space of densities, the quotient space, as an infinite dimensional Fisher-Rao information. So perhaps the last thing that I can do here. So one has to do the calculation in order to show this, and I'll skip it. But I can maybe draw a picture that will be similar to the one that I started with. So we have a similar situation, therefore. If we take diff n as the big space, and we equip it with this degenerate right invariant metric. Now we also have here the fiber, and we look at the quotient. Then this metric drops to the quotient, and on the quotient here we get this infinite dimensional Fisher-Rao metric, which is the descended H1 dropped to the quotient as a non-degenerate metric, so that the picture, actually the map here is the phi, but I can take this as the projection. And what we have therefore on the quotient is something like H1 dot optimal transform or infinite dimensional geometric statistics. Yeah, so I think I'll skip the derivations.
Thank you. Are there any questions?
So in finite dimensional situation, complete integrability usually means that you walk around some torus, true? And so what happens here? Here you always blow up somehow. So what happens?
Right, so this is, okay, they blow up. So these are the geodesics, the great circles. So this immediately brings up the following question, even in analysis, from analysis point of view. Is it possible, since I can look at, if I'm looking here at the geometry, I can of course imagine that it's possible to continue, should be possible to continue my solutions as geodesics, as great circles, beyond that time when, the blow-up time which I wrote here, in some weak sense. So it turns out to be not so clear how to do the analysis here. One thing we considered was to try to study this problem upstairs in the full group of diffeomorphisms by constructing lifts, the flows themselves. Now, something like that. So what this means is that I'm looking at the. I wrote, where is it? I wrote the solution here, rho, but one can just as well write the corresponding Jacobian, the Jacobians here, of the flow eta of T and x with respect to mu. And one of the things, the function, which is strictly positive until the blow-up time, but then it may become zero. It will always be non-negative because in fact it's the square of something. So one problem what can be considered is trying to see if it's possible to somehow make sense of continuing the flow past the point where it's zero. Now this was in fact in a way considered by Gromov and Eliashberg. There is a paper from the 70s, which I suppose was the origin of the H principle. I forget now the title, where they considered this kind of situation, but one does not get a diffeomorphism, or even one gets some kind of map, but it's difficult to make sense of all these other objects that I would like to associate with such a flow, like solutions of the corresponding PDE and so on. So, integrability. This is one possibility.
What is the official definition of complete integrability?
In I think the best one I know of is that you can actually completely explicitly solve the equation. Of course, you have different notions. You have the different hallmarks of complete integrability include bi-Hamiltonian structures. So, for example, Poisson structures that form the Poisson pair, from which you can derive the equation. And they have to be Poisson pairs, means they have to be related. Another point of view is to construct line specs. Well, it's not so easy to construct even in finite dimensions, but in principle, yes. So it will be basically like proceeding like in finite dimensions. But I don't know really how to. I haven't thought, very precisely, and I don't think it's actually even available in the literature in finite dimensional things. The other possibilities to construct the commuting infinite series of very simple things, which can be done, and just like in finite dimensions.
Another question?
You said here optimal transport like flow. So is this H1 version describable as optimal transport?
Well, I only meant here by analogy. Yeah. So we have not. This is still, there are many questions that we have not addressed, but at least at this point, the analogy would be that this H1 metric, which geometry, which descends to the quotient, gives an interesting distance function, which is being considered in statistics rather than optimal transport.
Right.
So, in other words, rather than saying, when I write H1 optimal transport, I should really perhaps writing infinite-dimensional geometric statistics. That's right. Statistical interpretation is clear. And it seems to be the infinite-dimensional generalization of what people saw as, these finite-dimensional pieces.
Right. So you've embedded the picture into the statistical sphere, I say. Right. And is it possible to describe, without saying geodesic flow on the sphere, is it possible to describe statistically the PDE?
The solution
You see,
is
when it's in this open set coming from H1, it's just whether that's the geodesic flow on that manifold. But when it goes in and it becomes secretly the geodesic flow in the sphere, forget that for a second. It has statistical interpretation. So can you describe the flow statistically? This is a line of giving a weak description of the PDE without using calculus, use statistics.
Yeah, I have
You understand what I mean?
Yeah, I can.
Because it's there.
Yeah.
The whole space, the whole flow is there, and on this piece of it, you describe it with PDE, right? And it extends, it has this other existence.
Yeah, I haven't.
And everything is there, because you have to describe statistically the flow there.
It seems to be possible.
Let's thank our speaker again. We will meet back in 10 minutes at 3:20.
Cedric Alani's field goal citation, they refer to his work on optimal transport in the first part of the talk.
Who did you mention?
Cedric Alani.
The line. Yeah. Well, easy. this is, we have not yet, of course, this is one of it's an interesting, very interesting connection. We have not thought this through. The one difference we see immediately is that there is some kind of rigidity here. Is some kind of rigidity. Namely, it doesn't matter what manifold I start with. Here. When I consider just this H1 dot metric, then I always end up with having, this infinite sphere.
That's always intractable.
That's right.
It's always the same thing.
That's right. So it doesn't seem to be giving me any possibility of using these infinite dimensional structures to actually say something about, for example, Ricci curvature, the curvature of the finite-dimensional manifold. But
unless it was a good concept, because that was back at optimal transport, right?
that's right.
Before the H1.
Yeah. Yeah. That's before the H1.
This is a comment, a question. According to Calabi, when Monge wrote his paper about optimally transferring a pile of sand from one place to another, he really was thinking about how to optimally move an army.
All right, next talk at 3:20.